This is a guided reading for Chapter 11, Section 1. So go ahead and get out your book and turn to page 285. And on page 285, read the first three paragraphs there. Read page 285 as an introduction. So pause the MP3 and then come on back. All right, welcome back. Turn to page 286, and you're going to read throwing a ball. It's about 3/4 of the way down a page. It's highlighted in red, throwing a ball. The analogy or the example up above with cash flow I found confuses students. But this is how work and energy relate. So we talked about the work energy theorem before, W equals delta KE. Well, this is looking at the system of the ball and seeing what impact does it have. So go ahead and read that. The throwing a ball, just what's on page 286. Pause it and then come on back. Okay, welcome back. On the throwing a ball, if you look at the picture on 286 at the bottom where it says throwing a ball, begin, end, figure A, you'll see that when you're throwing a ball, if you think about it, your force of your hand when you're throwing something is in the direction the ball is going to move. So we talked about it. If force and displacement are in the same direction, then the work done is positive, and you'll see the direction of the displacement drawn there with a green arrow, and then work done greater than 0, and the force drawn in a blue arrow. Well, if we want to find the kinetic energy of something after, okay, remember work equals change in kinetic energy, so W equals KE final minus KE initial. Well, you can rearrange that equation to get what they got below, which is KE before plus work equals KE after. That's where the purple bar graphs are at. So if you notice, if the ball was at rest before, there was no initial kinetic energy, but when you do positive work on it, you're going to end up giving it kinetic energy after you have applied that force over a displacement. Also, this equation for work, remember, is a constant force F. Okay, so if your force is changing, then it's a different ball game, but we're assuming a constant force over that displacement. Take a look at figure B, and you'll see catching a ball, and this is like when it's hitting you in the mitt. Okay, so if you got your mitt on and you're catching the baseball, well, think about it. The baseball is moving one direction. The force of your hand or the mitt on the ball is in the opposite direction. So take a look at the green arrow and the blue arrow. The green arrow is for displacement. Blue arrow is for the force, and they point in opposite directions. Therefore, the work is less than 0, or it's negative. So in this process at the end, you had kinetic energy before it hit your mitt. In the after, if you caught it, it's not going to be moving, so there's no KE after, and the work done is negative. If you add those two up, the positive kinetic energy before, the 1/2 mv squared the ball had right before it hit your mitt, plus that negative value for work, well, the bar graph denotes they're the same size, and it should end up as 0. On page 287, you're going to read that catching a ball. I interjected in the middle to hopefully make sure you understood those pictures. Go ahead and read catching a ball, pause, and then come back. All right, if you have any questions on the throwing or catching a ball example, please just find me for a minute or two, and hopefully I can answer those. All right, you're going to skip the section on 287 that says kinetic energy. That has all to do with rotational stuff, which will not be on the test. So flip to page 288 and read the first two paragraphs on page 288. So pause and then come back. All right, welcome back. We've talked about one type of energy, kinetic energy, energy of motion. Now we have another type of energy, stored energy, or what we'll call eventually potential energy. And they gave you some examples of that. Okay, you're going to read the section on gravitational potential energy in its entirety. But before you do that, a couple of things. Take a look at the bottom of page 289. There's a picture there that I don't like. Okay, there's going to be a lot of discussion about reference levels in what you're reading. Reference levels are up to you. You get to pick in terms of height. Okay, so think about something moving up and down. You get to pick what you're going to call 0 for height. Okay, that's what we're going to call reference level. You get to decide what 0 is. Well, my advice is always make 0 the lowest point in whatever problem you're doing. So, for instance, if you're tossing a ball up and catching it, in your hand at the same level, you'd call your hand 0. If you were tossing a ball up and letting it go down and hit the ground, you'd call the ground 0. We've been doing that all along. I just haven't told you when we've been doing projectile problems. I've always been calling the lowest point in a projectile problem, that's 0 in terms of height. If you do that, it'll make it so that you won't ever have to worry about any type of negative energy. All kinetic and potential energy or potential energy will always be positive, okay? And that'll make our life a lot easier. So just always call the reference level or the place where you're going to call 0 for height the lowest point. So do not do what they're doing at the bottom of page 289 in terms of their picture. One other thing when you're reading, and that is eventually we're going to consider the energy of a system. Okay, and remember, system is just basically what you're drawing in your picture. So like in our conservation momentum problems, the system was the 2 cars. Okay, and then sometimes we included the earth as well. When we're doing conservation of energy problems, which is the next thing we're going to do, you're going to include the earth in the system. Okay, but go ahead, read that. So pause and read the section on gravitational potential energy, and then come on back. All right, welcome back. If you got a little confused on the whole system thing and what we're gonna call it, it's not the end of the world. You'll see in problems how we're going to use it, and then I think it'll become much, much more clear. Also, the equation for potential energy is mgh, and there's a case for that. If you think about the work being done, force times displacement, if we're talking about the work being done by gravity, mg is the force and h is the vertical or the y displacement. So mgh, if you understand W equals Fd, potential energy being defined as mgh shouldn't be a big leap of faith there. It does make sense. On page 291, you're going to read elastic potential energy. Just read it. Okay, it'll come up in a couple of problems here or there, but just go ahead and read page 291, and also read page 292. There's a little bit of information there about, it's a continuation of the other page, but it's also, there's a little bit there about rest energy. So read that, and then come on back. Welcome back. On page 292, at the bottom, the equation for rest energy, E equals mc squared, is a big deal. We'll watch a video where you'll see why this is such a big deal or what this led to. If you're wondering, that rest energy is different than the potential energy. Okay, what we're going to be doing with our conservation of energy problems are macroscopic. In other words, we're going to look at like an entire basketball. We're not going to be splitting the atom, and we're not going to be looking at a molecular level. So this mc squared, yes, it exists, but you're never going to have to worry about it unless you are working in a nuclear power plant, so or on weapons. So we're not going to be using that in our problems where we're throwing something up, etc. However, the results of this are dramatic. If you take a pen, or better yet, take your physics book and take the mass of your physics book times the speed of light squared, which you can look up in the book, and figure out how much energy that translates into. And compare it to something like dynamite. It's more than enough to cause an explosion that would wipe out Kansas City. So there is a lot of energy associated with mass. You've heard of conservation of mass before. Well, soon we're going to learn in section 11.2 about conservation of energy. And really, mass and energy are conserved. They can actually go back and forth. That concludes this guided reading.